Okay, so I'll quickly share my screen. So, hello everyone. Today I'm gonna be talking about IP Cracker, which is about breaking intellectual property encapsulation on MSP430 devices. This is a project uh, done by me and Nandita Singh. So, what is IP encapsulation? IP encapsulation is a trusted execution environment provided on Texas Instruments MSP430 family of microcontrollers. Studying the security guarantees of IP encapsulation on MSP430 devices is important, as MSP430 is the most popular 16-bit low-power commercial microcontroller line. So, what does IP encapsulation mean? IP encapsulation segments the on-chip memory into secure and non-secure regions. Any read or write accesses from outside the IPE segment is restricted by the memory protection unit, as you can see in the functional block diagram on the right. IP encapsulation also disables JTAG or direct memory accesses. However, one should note that IP segment accesses by JTAG are restricted, but JTAG can still send run and halt signals to the device when the secure process is running. Finally, only a mass erase can remove the IP segment. So, what is the fatal flaw in the design of IP MSP430 devices? About 6 months ago, while reviewing the avant-garde security techniques supported on low-power microcontrollers, we came across a fatal flaw. IP encapsulation doesn't protect the register file. Also, no secure context switches are ensured between calls from non-secure processes to secure processes. This provides the capability to exfiltrate the entire IP protected memory, as I'll demonstrate in a couple of seconds. So this is the high level overview of how our IP attack is gonna work. And I'm gonna do a demonstration to show this. So let me just quickly switch over to this. Uh, okay. First, I'll set up the IP zone. And that is done. Now, before talking about this, let me talk about my debugger shell script. So what is a debugger shell script? So using a debugger shell script, I can asynchronously send run and halt signals to the device while also debugging the program on the device. So uh, as you can see, what this does is that it sends run signals and then it sends a halt signal to the device, and then it takes a dump of the entire register file and writes it to an external file, and then it sets the program counter back the start of the main function, and this process repeats. Uh, Now we need another capability to ensure that this works. We need a timer module. So what the timer module does is that it interrupts the program, the secure process when it's running uh, at every clock cycle. And the timer module ISR uh, is set up by us, that is the attacker. And so it sends the control of the program to outside the IP zone, where it basically traps the program without corrupting the register file. And like when the program is trapped inside the ISR, the debugger will halt the device and then take a dump of the registers and then send the program execution back to the start of main. And then we just simply increment the timer module value to 2 clock cycles. And then repeat the same process, and then we keep on doing this again and again and again. And this way, we are able to go one clock cycle deeper into the secure process every time. So I'll quickly take a dump and show you how this works. So now my debugger shell script is running. And by the way, I'm performing all my tests on MSP430 FR5994, which is an FRAM device. Uh, and I'm using the GNU GCC compiler. Yeah, I think the dumps are done. Uh, so uh, quickly show the dump that I took. Yes, so as you can see the program counter changing with respect to the stack pointer and all the other general purpose registers. So using this, we will now reverse engineer and try to get the assembly stored inside the IP protected zone. So uh, this is the actual dump I got from the AES 128 algorithm I'm trying to attack. And so this is basically a very big dump. And I'm gonna do some post processing on this. And what it does is basically it tries to get the best guesses from the register file information. Uh, so as you can see, like it has done some guesses, like this is an increment instruction on, and the value is stored in the R14 register. Uh, also, so now the kind of instructions that we're interested in to get the entire memory dump are actually memory to register operations, where memory location, data from some memory location is transferred to the actual register so that we can read it from the register file and we can control the location of the memory location that we provide in this instruction. So how do we find out such instructions? Let me give you an example of one such instruction. Yes, right here. So now this is a partial guess for that instruction. We know that the R14 register is changing, but we're still ambiguous on what kind of an instruction it is because it doesn't match any of our algorithms. So what we can do is we'll simply do some more tests. So I did some more tests, and as I said, there are no like secure context switches between calls from regular processes to secure processes, so we can directly jump to the targeted instruction. So the instruction which we are suspecting to be a memory to register operation, we just like give it this data, and then we get something like this. As you can see, only the R14 register is changing, and we had provided it an address location outside the IP zone whose value we knew, and its value changed to this. So now we know it's a move instruction from a memory location to the register. And using this, we can get the entire memory dump. So this will be our ROP gadget. This is the setup of our ROP gadget. The ROP address is basically the base address of the IP zone, and we keep on incrementing it uh, to get more dumps. So I'll quickly run this for you. As you can see, we got the IP dump and we are successfully able to exfiltrate the data from the IP zone. Now, moving on. As you can see, the test results, all the compiled assemblies leak the secret at all compiler optimization levels of GCC compiler. And so why does IP encapsulation fail? Two reasons. One, as mentioned in Aegis Architecture, the paper on Aegis Architecture by Edward Su and others, that the privacy of registers and on-chip caches should be protected by trusted computing base from software attacks. Otherwise, an attacker could simply reverse engineer it and exfiltrate data from the secure computing base. Another one is that secure context switches between processes should be enforced. So how can we solve this? This the possible mitigations that we're working on right now are uh, like software based. You could like compile make a compiler which only produces assembly, which only produces memory to memory operations. Or in certain applications, this won't work for all applications. You could erase the IP encapsulated memory at boot time. Hardware or microarchitectural mitigation strategies would involve saving the register file to a protected memory area and clearing it before an untrusted interrupt handler starts. Or we could use an ARM trust zone like gateway veneer between calls to ensure that there are secure context switches from regular to secure processing. So yeah, that was it. Thank you.